What's cracking, y'all? Welcome back to the LANA Algorithm example 2 circuit. Let's get right to step 7, which is to ground the circuit. Remember that when we were actually measuring the individual entries of our node voltage potential vector U sub G, each of these entries was measured with respect to a chosen ground node. The choice of ground node is arbitrary. We could choose any of the 7 nodes. What's important though is that every voltage measurement is made with reference to that ground. In the physical circuit build scenario, what that means is if we choose, let's say, ground node to be node 7, we attach the negative lead of our multimeter to node 7, and then we move the positive lead, node 1, node 2, node 3, node 4, node 5, node 6. We could also move it to node 7. The negative lead never moves. That node to which the negative lead of our voltmeter is attached is called the ground node. The fact that we're shuffling around the positive lead to make node potential measurements implies that every individual entry of the voltage potential vector U sub G is with reference to this ground. And for those of you that actually did some of the experiments early on, you'll notice that when we ground the circuit, the measured value of ground node is always 0, because when you take a voltage potential relative to itself at a node, there's no voltage change at any individual node. That's why leads have no electronic behavior all along the same piece of wire. There's no charge difference on that wire. In the linear algebraic nodal analysis algorithm, we break the process of grounding the circuit into 2 substeps. The first subset is to choose any node arbitrarily to be ground node. Another word for ground node is datum node. I've also heard it called a reference node. I'm going to use a D for the individual node in our node set that we choose to be ground. In this case, we're going to choose node 7, so I highlighted it in orange to make that really clear. That is the node to which I attach the negative lead of our multimeter. It's my ground node, or another way to say that it's the datum node. Another way to say that is it's the reference node. All other nodes are non-ground nodes. Mathematically, we can model the idea that all entries of our node potential vector U sub G are made relative to our ground node by assuming that the associated node voltage potential variable is equal to 0. In this case, we said that the datum node we're going to choose is node 7. We'll go ahead and highlight that in orange. And then what we're going to say is U sub 7 or U sub D is equal to 0. If we were to actually measure this on the circuit, as mentioned previously, if I touch the negative lead to node 7 and the positive lead, there is no charge potential difference anywhere along that wire, and we'd actually get a physical node potential reference value of 0 volts. I do want to be careful and say that just because we're setting this equal to 0 doesn't mean that's equal to earth ground. The ground node doesn't necessarily have to have 0 volts with reference to what we call earth ground. It's just that what that says is this is the origin of our measurements. All measurements will be with respect to this node. This is similar to setting the origin in a frame of reference in Newtonian dynamics in the sense that the location of that origin tells us what positive and negative values means once we know where it is. But this assumption shifts one of our node potential variables from unknown to known. The reds are all unknowns. The moment that I assume that my ground node has potential 0, that variable is no longer unknown. It is known by mathematical assumption. In our schematic, when we ground node 7, we can draw a little symbol, which is a little line followed by a bunch of other lines. I've also seen it where it can be written as an upside down triangle, equilateral triangle. You could fill it in or not. But that means, hey, listen, that's ground node. The moment that we assign ground node, we get one variable reduced for our entire system. We shifted that variable from unknown to known, which was part of the whole reduction process that we wanted. We wanted to go from the large collection of variables and equations to a smaller collection that would completely describe the electric behavior of the circuit that we're analyzing. Recall back to step 5A of this algorithm, which was the node potential form of Kirchhoff's voltage laws. What we did is we encoded the voltage drop across each element in our circuit as the difference between the node potentials on either lead of that element. For example, for resistor 1, we said that the voltage drop across resistor 1 was going to be positive U1 minus U7. So 1 times U1, all zeros, minus 1 times U7. That gives us that voltage drop. That was kind of nice because when we actually lined up the columns of this matrix, we did the columns by nodes. And that's really, really nice because when we do U1, it gets associated with the first column, U2, the second column, U3, the third column, all the way down to U7. But we're claiming that grounding the dth node, in this case we chose D equal to 7, so grounding the 7th node actually has immediate ramifications algebraically in this process. In order to better understand what that means, let's go ahead and focus in on the matrix vector multiplication problem, the incidence matrix times the node potential vector. This thing gives us the vector of voltage drops. Remember that we said when we have a matrix times a vector on the right-hand side, we can take linear combinations of the columns of the matrix with scalar multiples defined by the individual entries of this right-hand side vector. Now, I've color-coded them, so U1 is going to get mapped with the first column, U2 is going to get mapped with the second green column, U3 the third pink column, all the way down to U7, the last orange column. The corresponding linear combination that we're going to get looks exactly as you see on screen, where we take a linear combination of each individual columns of our incidence matrix aligned with the associated node potential variable with the appropriate column. Again, the nodes of this matrix align with the columns, and so that's really, really nice that we've ordered it this way. We're claiming that when we ground node 7, that variable gets set to 0, which means that that U7 is no longer unknown, it is known, and it is 0. But remember, scalar multiple zeros times any vector behave very, very beautifully from the standpoint of doing algebraic work. More specifically, when we bring that 0 into this vector, all the entries of the vector are annihilated because 0 times any scalar is 0, which means that the contribution made by node 7 to the Kirchhoff's voltage law disappear. Those are no longer involved in any of our voltage drop calculations. But this is one of the mathematician's favorite tricks. Adding 0 does nothing. We can literally disappear those zeros from this sum, and we're left, instead of a 7-term sum, we're left with a 6-term sum by our assumption that the ground node has 0 potential. Notice that grounding process that happened in the schematic actually laid out to have two separate representations of our voltage drop vector calculation. The same variables on the left-hand side are either equal to the entire circuit. This is why I put the little G there. This incidence matrix includes ground. This one down here does not include ground. In particular, my dimensions on my node potential vector have transformed from 7 times 1 into 6 times 1, and the last entry of that vector disappears. It was only the last one because we chose D equals 7. It could have been any of these. If I would have grounded node 2, this node would have disappeared, and the appropriate second column of that matrix would have disappeared when I wrote this out. But the fact of the matter is, check it out, the inner dimensions went from 7 to 6, or n sub g, to n sub g minus 1. This implies that the act of grounding our circuit does algebraic work by literally just eliminating an entry of that vector and an entire column of that matrix. I'm going to make a claim, however, that we can accomplish such a reduction using matrix vector multiplication by eliminating the appropriate row of that matrix. Remember, when we do algebraic work on the rows of a matrix, we multiply on the left-hand side. Here I have the original node potential vector U1, U2, U3, U4, U5, U6, U7. I want to eliminate the U7 because it's not useful once we've grounded that circuit on node 7. If I wanted to leave all rows untouched, I would multiply on the left-hand side by an identity matrix. But in this case, I want to delete the dth column, which means if I take the ng times ng identity matrix, in this case, the 7 by 7 identity matrix, and then delete the dth row of that matrix, in this case, the 7th row, check it out. That would give me one copy of the first variable, one copy of the second variable, all the way down to one copy of the sixth variable. When I look at the appropriate last row, there's no entry. In other words, the way that we deleted that ground node is literally to multiply by a matrix that reduces the dimensions of that vector. I will call that a deflation matrix out of respect to my PhD advisor. My PhD advisor did some work in band Lanczos and band Arnaldi algorithms. Don't worry about that. But one of the things that I learned from that was deleting dimensions. It's kind of nice to think about that as deflation, like deflating a balloon, right? If I deflate a balloon a little bit, it lets some air out of the balloon. If I deflate this vector, I let some air out of the vector. I actually get rid of some dimensions. Because linear algebraists have a penchant, a proclivity, a deep love of column vectors, we are going to define the grounding matrix or the ground node deflation matrix to be the identity matrix minus the dth column. So the 7 by 70 identity matrix would have 7 rows, 7 columns. The main diagonals would all be 1. In this case, we've chose D to be 7. So I take the 7th column of that identity matrix and then literally just disappear it. That means instead of 7 columns, it has 6, and the last entry disappears. Remember, left multiplication manipulates rows of a matrix. So that means that I'm going to take the transpose of that matrix and multiply it by U sub G, and that would give me my reduced grounded node potential vector where the dth entry is deleted. But here's a claim. Not only did I want to delete the dth entry of my node potential vector, I also wanted to delete the dth column of my incidence matrix. Remember, left multiplication by matrices manipulate the rows, right multiplication manipulate the columns. In other words, to get rid of that dth column, I'm going to multiply on the right by that grounding matrix, by that deflation matrix. That is exactly step 7b, which is to ground the incidence matrix. I start with my original entire incidence matrix, which includes the ground node, so the G is included. When I set G to 0, that means I'm zeroing out ground node, which means I'm going to delete that dth column of that matrix. Deleting the dth column of the matrix means multiplying on the right-hand side by my grounding deflation matrix. There it is. This grounding matrix has one less than the number of nodes in my original circuit because I've deleted ground node. This one has all the nodes in the circuit. That associated grounded incidence matrix has the dth column deleted. That is this matrix right here. Let me repeat that in a different way. In order to form this grounded matrix, we're going to take our original incidence matrix, which includes all nodes in our circuit, and delete the dth column of that. So here we go, 1, 2, 3, 4, 5, 6, 7. There's the identity matrix with the dth column deleted. Look at, I take one of the first, one of the second, one of the third. When I get down to the dth, there's no pull off. I'm not picking off that column, which means when I do the multiplication of the grounding matrix times the incidence matrix, I get the reduced or grounded incidence matrix with no reference to the ground node. But remember, our enumeration scheme allowed us to block partition the entire incidence matrix by element type. So the first M sub R columns were all resistors, the second M sub V column were all voltage sources, and the third M sub I columns were all current sources. So I actually have a blocked partition version of that matrix, and the number of columns in each of those subblocks matches the number of rows in the grounding matrix, which means I can actually bring that grounding matrix into the individual subblock pieces. Let me make sure I'm not smoking anything. That actually works out. A sub RC times D sub 0. Here's the resistor subblock of our incidence matrix. There's the grounding matrix. When I multiply those two, it just deletes the last column of that. That gives me a smaller one. We're going to actually define subblocks of our grounded incidence matrix, the one where G is set to 0. And that subblock will be A sub R0. A sub Rg is the entire incidence matrix associated with the resistors in our circuit with ground node included. When I set G to 0, that is the resistor subblock of our grounded incidence matrix where we assumed G equals 0. Similarly, when we pull D sub 0 into A sub VG, I have A sub VG times D sub 0. That's going to be the grounded voltage source subblocks of the grounded incidence matrix. But like reading Rainbow, don't take my word for it. Check that out. We have a 2 by 7 matrix because there were 2 voltage sources and 7 nodes. When I multiply by the grounding deflation matrix, I delete the last column, or the dth column in general. That column disappears and I'm left with the grounded voltage source subblock. We call that A sub V naught. Because we haven't permuted any rows in my grounded incidence matrix, that V naught sits in the same location as the A sub VG. And finally, we account for the grounding process on the current sources. We take the current source subblock of the entire matrix, multiply it by the grounding matrix, and then we get the grounded current source subblock. Those dimensions work out in general. Don't trust me. We can actually test it for this circuit. Take the current source subblock, delete the dth column, decrease the dimension by 1, and then we get the grounded current source subblock. All this work was to define the grounded incidence matrix. Let's define a new dimension, which is the number of nodes in the circuit, not including the ground node. So we'll call that n sub 0. When we set G to 0, we get rid of the ground node. With that, we have our grounded incidence matrix was the entire incidence matrix times the grounding matrix. That was partitioned into subblocks based on element type. The grounded resistor subblock is the entire resistor subblock times the grounding matrix. Same thing with the voltage sources, same thing with the current sources. This operation was literally to delete the dth column of the appropriate matrix subblock. And the reason that we deleted the dth column is that when we set that ground variable to 0, it disappeared from our calculations in Kirchhoff's voltage laws. And with that, we've completed step 7. We decrease the number of nodes by 1 when we set ground to 0 because it disappears from the circuit. We decrease the number of unknown node voltage potentials because when we ground the dth entry of this, it gets set to 0, so it shifts from unknown to known. If we want to get rid of a row, we have to do left multiplication. In this case, we do it by the transpose of the deflation matrix. We also decrease the column dimension of our incidence matrix by deleting the dth column of that. When we want to delete columns, we do it via right multiplication. The deflation matrix or ground matrix associated with grounding our circuit is literally the n sub g times n sub g identity matrix, where we've deleted the dth column of that, the column associated with ground node. That has ramification for the subblock partition. We can subblock partition the grounded incidence matrix very similar in the way that we subblock partitioned the entire incidence matrix based on element type. When we're multiplying on the right, literally we're just deleting the corresponding dth column of each of those individual subblocks. These structures set us up really, really nicely to actually now go back into the circuit equations that we did in step 5, A, B, and C, and ground those equations. Delete all reference to ground node because we've set that node variable potential to 0. That's exactly what we're going to do in step 8, which is to stay grounded. I'll see you in the next video.